So let's take a look at a reaction here and apply some organic chemistry concepts to that reaction, right? So ideally you've watched a couple of these videos or you've spent some time understanding things like electronegativity and bond polarity and nucleophile strength. But here's a reaction and we'll kind of compare it to. So maybe you already recognize what's going on here, and that's one way to kind of know how these reactions work. Is just recognition. You can say, oh, well, I've replaced a bromine with an alcohol group. This looks like a substitution. That's correct. And this also looks like maybe it all happened in one step. You know, there's quite a bit more detail there we won't go into here. Right? This is an SN2 reaction, if that's familiar. Then you kind of can path this reaction out, perhaps, you know what's going to happen. But you know, that's not the only way to figure these things out, though. There's other ways to do it. So let's go back towards our organic chemistry concepts. You can say, a bunch of carbon-carbon bonds. I've got a full charge hydroxide here. I've got a carbon bonded to a bromine, right, by periodic table, and you can look it up or get used to it and say, well, actually, bromine's a little bit more electronegative than carbon, right? So if we're looking at something that's going to do something, right? Yeah, our carbon hydrogens in the skeletal structure don't really do much in terms of chemical reactivity. They're pretty stable and neutral and not much goes on, right? But bromine is more electronegative than carbon. It's actually pretty close if you look it up, but it's more electronegative, which means that bromine's going to pull some electrons away from carbon and be partial negative, right? But since it's stealing carbon's electrons, carbon is going to be partial positive, right? So I've got a dipole here, right? And dipoles kind of help these reactions go because if I have something charged, it can help something else charged kind of come together, right? Opposites will attract and similars will repel. This hydroxide coming up near this partial negative bromine, there's not going to be a good interaction there. They'll kind of repel each other. But if this hydroxide finds its way over to the carbon, that's where the reaction can happen. So you may be already familiar with SN2, nucleophile, attacks, breaks bond, and we've substituted that on there now. Right, and that's an SN2 reaction. Without going into the details, there's quite a bit more to that. Right, but why does this reaction happen in the first place? Well, it works in part because you have a dipole here, and that you need something more positive here to attract that nucleophile in the first place. Right? There's also principles of reversibility. So, okay, well, on this way, my new product here, this oxygen is more electronegative than carbon. Right? Why doesn't this negative bromine just come back in, bump it back out, and get you back to the start? Well, it can. It's just not very favorable. So if we're comparing molecules, yeah, you've got negative charge hydroxide here. That's a nucleophile. Negative charge bromine here. That's also a potential nucleophile, right? But which one's better, right? That's going to determine whether this reaction goes forward or backwards. If I make a stronger nucleophile in the end, then why wouldn't it just react, right, and make something else or bring me back to the start? But bromine's not a stronger nucleophile, and you can memorize that, or we can kind of understand those periodic table trends, which will come in handy for lots and lots of reactions. So what makes something a stronger nucleophile, right? That was imagining carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, kind of writing all over my mechanism here, right? But these charged molecules, as they get bigger, right? So bromine is a lot bigger than hydroxide. As they get bigger, that single negative charge is spread out then over a whole range of space compared to hydroxide. And so spreading out charge is way more favorable, right? And that's going to mean this is going to be a weak nucleophile, weaker than hydroxide. So in general, the weaker nucleophile isn't going to do a reaction and make something stronger, right? It's hard to react and make something more reactive in the end, right? Without a lot of careful planning and tricks to kind of make something like that happen. But yeah, so the nucleophile strength, the electronegativity, the bond polarity, all those come into play in even a one-step reaction like SN2. And so the power is being able to kind of understand the concepts so it makes sense and you're not just drawing random arrows and kind of memorized plans. And that's sort of the key, because then we can apply all these things to just about any reaction we do. The majority of organic chemistry reactions are going to involve a nucleophile, an electrophile, a nucleophile, a leaving group. You know, if it keeps going, it keeps going. If you memorize some key concepts, it makes it a lot easier to kind of figure out where things are going to go.